Okay, so let's work on this problem involving arsenic acid. And you're given here the three Ka values, given that arsenic acid is a triprotic acid anyway. So that just means that arsenic acid has three stepwise reactions in giving up the proton, or the protons. Okay, the first reaction should be the abstraction of the first proton by water. Okay, so this one should be H3ASO4, and I'm not gonna write here the phases of the solution anyway, just to save some time and space. Okay, and this is plus H2O is equal to hydronium ion concentration, or hydronium ions rather, plus H2ASO4 minus. Okay, this is a value of Ka1, which is given in the problem. Okay, and then the second one should be H2ASO4 plus water. Okay, which will give you H3O plus HASO4 2 minus. That's given with a Ka2. Okay, and then lastly you have HASO4 2 minus plus H2O is equal to H3O plus the arsenic ion. Okay, and this is given by a Ka3. A few things to notice before we move forward. So keep in mind that Ka1 is greater than Ka2 is greater than Ka3. Therefore, the weakest acid here should actually just be these species, or this species. Okay. Also note that these two species are amphoteric. Okay, that's not the concern of this problem, but just a heads up. Okay, so these are the three reactions that we're gonna consider. We have to write separate ice tables for this one. Okay, and again, notice that Ka1 is the largest value of among the three Kas. Okay, so that's important to know, especially when we calculate for hydronium ion concentration later. But let us first calculate for the first Ka. Calculate how much concentration of hydronium, or well, H plus. It's the same thing. And this we have at equilibrium. Okay, so let's erase that for now. Okay, and then to write the ice table, we have molarity here, and then ICE. Okay, then we are beginning with 2 molar of arsenic acid. Okay, so 2.00. Okay, and then again ignore water, and then 0, 0, and then here we have minus x. Okay, when the system is about to reach equilibrium, this is x and this is x, and then this one should be 2.00 minus x. This is x and this is x. Okay, we can write next an expression for Ka1, but let's make this calculation simpler first by assuming that this is actually just equal to 2 molar, meaning that x is negligible. Okay, so if we do that assumption, then we're just going to end up with Ka1 is equal to 5.5 times 10 to the negative 3 is equal to the concentrations of the products multiplied by each other. So that's hydronium times H2ASO4 minus divided by the concentration of arsenic acid. So that is 2.00. Okay. And if we actually solve here for x, x should actually give you 0.105 molar. Okay. Now, to do the percent dissociation, we just divide that value with the original concentration 2 molar. So the percent dissociation should just be equal to 0.105 molar divided by 2.0 molar and times 100%. Now this one actually gives you 7.5%, which is well above the 5% rule. So this just means that x is not negligible. Okay, x is not negligible, or meaning our assumptions are bad actually. So what we'll just have to do is rewrite the value of rewrite the expression for Ka1, except that this time we cannot assume this anymore. We just have to write this as the concentration of arsenic acid. Okay, so that one will now become 5.5 times 10 to the negative 3 is equal to, again, x for hydronium ion concentration, and then x for H2ASO4 minus concentration. And then this one's divided by 2 minus x. Okay, if we simplify this equation, we're going to get, and I'm going to get rid of the scientific notation. So this is going to be 0.011 minus 0.0055 x. Okay, this is just the same numbers, by the way, just in case you're curious. And then this is equal to x squared. Okay, and then to rearrange this so that we can use the quadratic formula, we will get x squared plus 0.0055 minus x, and then 0.011 is equal to 0. Okay, so that's going to be the equation. Let me just rewrite that. X minus 0.011 is equal to 0. Okay, from here, again, the quadratic formula is equal to x minus b plus minus square root of b squared minus 4ac, okay, divided by 2a. And here we have a equal to 1, b equal to 0.0055, and c is equal to negative, don't forget the negative sign, 0.11. All right, and we can then set up this equation. So x therefore should be equal to negative 0.0055 plus or minus square root of 0.0055 squared. Okay, and then 0.055 squared. Let's actually put the two outside. Okay, and then minus 4 times 1 times, times negative 0.011. Okay, again, don't forget the negative sign for 0.011, divided by 2 times 1. Okay, solving this will give you two x values. X sub 1 is equal to 0.102, and then x sub 2 is equal to negative 0.108. Of course, we reject the negative value, and what we get instead is 0.102. Now notice, by the way, that our assumption was correct-ish, because this is not really a number which deviates that much from 0.105. But we'd stick with this original value instead, or with this new value instead, sorry. Okay, now again, remember that Ka1 is greater than Ka2. Alright, so that actually means that if Ka2 is very little, remember that the equation pertaining to Ka2 is this equation, H2ASO4 minus plus H2O is equal to H3O plus HASO4 2 minus. Again, this is Ka2. Now since we know that Ka1 is greater than Ka2, then we can just assume that this H2ASO4 minus actually dissociates at a smaller concentration than arsenic acid does. Okay, H3ASO4. Okay, so that means that probably this concentration of 0.102, which, by the way, remember, corresponds to the concentration of hydronium ions, and that's also equal to the concentration of H2ASO4 minus. So this actually just means that it's actually the first dissociation which will ultimately dictate the pH. Okay, and again, H2ASO4 minus just barely dissociates. So we can still write an ice table for this one because we want actually anyway the concentration of HASO4 2 minus. Okay, so this is MiCe. All right. And again, we now have a new concentration for, or we have now a concentration for H2ASO4 minus. So that will be 0.102. Okay, and then ignore water. Now we do have hydronium ions already in solution as a result of the first dissociation. The second dissociation anyway will not happen before the first dissociation. So this one should not be a non-zero value, 0.102. This one should be 0, however. At equilibrium, you have the following changes. And then this one should just be 0.102 minus x. This one should be 0.102 plus x. This one should be x. Again, let's make our life simpler and assume that this is equal to 0.102. And assume that also this is equal to 0.102. Okay, and then we can write an expression for Ka, Ka2, such that Ka2 is equal to 1.7 times 10 to the negative 7 is equal to the concentration of hydronium is 0.102. Okay, times x, concentration of HASO4 2 minus, divided by 0.102. Okay, and we just cancel out here 0.102 because they're the same, and we actually find out here that the concentration x, which corresponds to the concentration of HASO4 2 minus, is just equal to Ka2, 1.7 times 10 to the negative 7 molar. Okay, if we again do the percent dissociation to just check if our assumption is good, so the percent dissociation here is equal to 1.7 times 10 to the negative 7 molar. Okay, divided by the initial concentration 0.102 times 100%, we get here a really small value, so 0.00012%, meaning that our assumptions are good. Okay, and then the next thing that we actually do, let me just add one more slide, is to rinse and repeat basically the same thing that we did here, and do the same thing for Ka3. Okay, and this time again note that Ka3 note that Ka3 is actually also less than Ka2, okay, which is again less than Ka1 as well. So this last part of the problem, wherein arsenic acid is actually giving up the proton, or the third proton, is really does not favor the dissociation, just because at this point you now have a doubly negative charged anion, that is HASO4 2 minus, and since you have a really negative value there, that just means that it's hard to let go of a positively charged proton. Okay, but let's do the math. So here again, let's write an ice table for the third dissociation, or for the third proton being given up. So this is HASO4 2 minus plus H2O is equal to H3O plus KSO4 3 minus. Okay, ice table. Again, this is for Ka3, by the way. We have this value from the previous equation that we just solved, so that's going to be 1.7 times 10 to the negative 7. Okay, and then this one should be 0.102. Okay, that's again from the previous problem. and then arsenate should be 0. Okay, now again, this value of 0.102 for hydronium just means that if the second dissociation did not contribute much to the concentration of hydronium, neither does the third dissociation. Okay, and then this one should be minus x at an equilibrium, plus x, then this should be 1.7 times 10 to the negative 7 minus x. Okay, this should be 0.102 plus x, and then there should be x. Again, let's just make the assumption this one will not even really use the quadratic formula anyway because of that small numbers. So this is 1.7 times 10 to the negative 7, and this is roughly 0.102. Okay, so here remember that the Ka3 is equal to 5.18 or 5.1, sorry, times 10 to the negative 12. So see how really small that value for Ka is, Ka3, and that should be equal to 0.102 times x divided by 1.7 times 10 to the negative 7. Okay, if we rearrange this problem and solve for x, what you're going to get is 8.5 times 10 to the negative 18 molar. And remember, this is the concentration of the arsenate ion. Okay, and again, if we solve for percent dissociation, just to see if we are following the 5% rule, so that's percent dissociation. Dissociation is equal to 8.5 times 10 to the minus 18. At this point, if you're not even asked for percent dissociation, I don't think you should even like calculate for it. Notice how really small that number is. Divided by 1.7 times 10 to the negative 7. Okay, times 100. Okay, this will give you, and this will give you 5 times 10 to the negative 9% dissociation. So our assumption is very good. All right.